So we're going to consider several matrices, and we will start for each matrix with the column space because I think it's the easier of the two concepts and therefore more elusive. But then, of course, we'll also do the null space, which is probably harder conceptually, but then easier to identify. There are more straightforward rules for exactly what you need to do to determine what the null space is. And the two concepts are equally important. So here we go. We have a 3x4 matrix. So here, to answer the question of the column space, you have to determine what it is that you can get out of this matrix by linear combination of its columns. So for us at this point, matrices are just vectors in Rn organized as columns into a table. So that's all a matrix is. We have not yet interpreted a matrix as a whole integral object. We haven't done that yet, and we won't do that for a while. And of course, the great power of matrices comes from thinking of the whole table of numbers as a single algebraic object. The matrix that you see on your screen right now is just a collection of 4 vectors in R3. We organize them into a table purely for convenience. It's just a set of 4 vectors. And so the column space question is, what can we get out of these 4 vectors by linear combinations? Similarly, when you look at a function such as sine of x, you can ask yourself, what can this function give me if I were to plug in various values of x? And the answer for sine of x will be any number between -1 and 1. That's called the range of a function. So the column space of a matrix is very analogous to the range. It's what you can get, but the function is linear combinations of the columns. So what can you get by linear combinations of the columns? And it's particularly special when you can capture it with a simple expression. So let's analyze, what can we get out of these columns? Well, the first column is 1, 2, 3. What can we get out of the first column? Just multiples of 1, 2, 3. Yes, great. Okay, let's look at the second column and see what it adds to the picture. What kind of ingredient is it? Well, it's not a new ingredient. It doesn't add anything that we didn't already have. It is useless when it comes to augmenting the column space. We can get with the first 2 columns precisely what we can get out of the first column alone, which is multiples of 1, 2, 3. And at this point, why don't we just capture it with a mathematical expression? That's nice. In words, multiples of 1, 2, 3. As a mathematical expression, alpha times 1, 2, 3, because alpha means any number. So we're literally looking at multiples of 1, 2, 3. Okay, moving on. With 2 columns, you get the same thing. Well, now we add the third column. So hopefully that will contribute something new. And it turns out, no, it doesn't contribute anything new because it's already a multiple of what we already had. That's a pivotal moment. Okay, pivotal realization is that the third column adds nothing to the picture because it's just a multiple of 1, 2, 3. So it's already in there, doesn't add anything. And the fourth column similarly adds nothing to the column space. So the column space is just a multiple of 1, 2, 3, alpha 1, 2, 3. That's what column space is. I think it's a very simple concept because it's strictly equivalent to the range of a function, except the function is linear combinations of the columns. The null space is not about what you can get out of the columns, but the relationships among the columns. Relationships among the columns. And here, there are actually plenty of relationships. The second column is the same as the first. That's a relationship. That's a linear relationship. That's a key right there to constructing a fancy zero, which is what we call it. And that fancy zero, how do we obtain it? it's column 1 minus column 2. That equals 0. More specifically, it equals this 0. 0, the vector. So the way we capture it is by saying any multiple of 1 minus 1, 0, 0. Okay, so that's a moment to pause and make sure you understand this. So it is an essential task to capture the fancy 0, the coefficients that give you the 0, that give you 0. And those coefficients are probably what I'm referring to as a fancy 0. Because it's not the 0 that matters, but how we get it. And here we get it by an interesting way. We don't just say 0. We just say take the first column and subtract the second. Okay. But there is another one. Comma. In a moment, we'll switch from a comma to a plus. That's a big difference, a comma or a plus. You know, but we'll talk about why I put a plus there. That's not just a comma, it's a plus. But let's first say the next thing we noticed was that the third column was 4 times the first or the second. Take your pick. I think it's best to relate it as 4 times the first, because I have a system. I always relate things to as leftmost a column as possible. I always go as far left as possible. So I will refer to the first column and say that it's 4 times the first column. What does that mean to us? It means to us that C3 minus 4C1 equals 0. That's a non-trivial linear combination that equals 0. That makes it a fancy 0. And the way we would capture it in a column by just peeling off the coefficients from the linear combination. Minus 4, 0, 1, 0. And then the fourth column came in and we said, well, that too is a multiple of the first column, and the same multiple actually. So the vector in R4 that corresponds to that observation is 4, or we can say minus 4, 0, 0, 1 in the fourth position. So these are all columns representing the non-trivial linear combinations of the columns in the matrix that equal 0 organized into a column. Okay, but why do we put a plus? That's very important. Why we put a plus here? Because null space is a space, right? If you have one non-trivial linear combination that equals 0, let me put it here. Let's say, not in this example, let's suppose that it was true that 7C1 minus 4C2 plus C3 minus 5C4 equals 0. And it was also true that 8C1 plus 5C2 minus C3 minus C4 equals 0. Well, then, look what I can do. I can add the left sides together and the right sides together, and I would have 15C1 plus C2, none of C3, minus 6C4 equals 0. Right? Do you see what I did there? I added the linear combinations together. And what did I get? Because of the 0 on the right-hand side, I got another non-trivial linear combination that equals 0. Are you beginning to see that closure under addition? Yes. If you take one linear combination that equals 0 and another linear combination that equals 0 and add them together, you get a third linear combination that equals 0. So there's closure under addition. So it has the makings of a space. Okay, what if I took the first linear combination and multiplied it by 10, both sides? Then I would get 70C1 minus 40C2 plus 10C3 minus 50C4 equals 0. Once again, equals 0. Because I just multiplied the 0 vector. It's 0 like this. That's what it equals. When I say 0, I mean 0 the vector. Right? I have another linear combination that equals 0. So these linear combinations that produce 0 are also closed under multiplication by numbers. So it truly is a space. And if I want to capture all possible things in that space, then I need to start calculating all possible linear combinations of these special vectors. So it wouldn't be complete to put commas in here, because it almost makes it seem like, well, it's just these vectors or these vectors or these vectors. Oh yeah? Well, how about 15, 1, 0, minus 6? Why is that not in the list? That's not fair. But when I put a plus here, that changes everything. That means that I can take any values for alpha, beta, and gamma, including the vector, if I just add the first two. Minus 3, minus 1, 1, 0 ought to be represented because it is a linear combination that produces 0. Minus 3, minus 1, 1, 0. Yet, without the plus, it's just not represented. So you need a plus. You need all linear combinations of these vectors. Now, you might wonder, what about
plus delta
0, 0, 1, minus 1, right? Because it is a true observation that the third column and the fourth column is the same. So why not reflect that? Isn't it underrepresented if you didn't do this? Well, first of all, let me explain to you why it wasn't underrepresented without it. And then I'll explain to you why that happened. Consider these two vectors here and subtract last from second to last. Subtract this one from this one. And do you see that you actually get exactly what we just had on the screen, which was plus delta 0, 0, 1, minus 1. So it's already in the mix. If you take beta equals 1, gamma equals minus 1, and alpha equals 0, you will get this vector. So it's already in the mix. Why? How is it already in the mix? We didn't specifically add it. Okay, well, we observed that the third column is 4 times the first, and we captured it right here. We then observed that the fourth column is 4 times the first, and captured it right here. But if you think about it, if you observe that the third column is 4 times the first, and the fourth column is 4 times the first, then you have also logically observed that the third column equals the fourth, right? If they're both 4 times the first, then they must be equal. So logically speaking, that information is already in there. So that's why we don't add it. And adding it would actually be a mistake. To have this is a mistake because previously we had a nice kind of uniqueness. There was only a single way to get any linear transformation that produces 0 out of this expression. There was only a single combination of alpha, beta, and gamma that produced it. Now we lost that uniqueness because, for example, to get this vector, we can now do it in 2 different ways. You can say alpha equals 0, beta equals 1, gamma equals minus 1, and delta equals 0. Or we could say the first 3 are 0 and delta equals 1. So we lost the uniqueness. And we lost the uniqueness because the observation, the information that was already in there was added one more time. You might feel a little bit unsure at this point because you might be asking yourselves, when do I stop? How do I know when to stop? And how do I know if all of the necessary relationships have been captured? And to give a complete exhaustive answer will take us a couple of weeks. But essentially, if the relationships that you're capturing include a vector that never participated before, then you're 100% sure that you're adding new information. So make sure that every linear combination that you're capturing by an expression in the null space includes a vector that was not engaged previously. You see here we engaged vectors 1 and 2. Here 1 and 3, so 3 was new. Here, 1 and 4. So every time a new vector was engaged. And that's why these 3 vectors ended up being linearly independent. So we want the vectors capturing the null space to be linearly independent. Now, for some matrices, it may not be so easy to do this on an intuitive level. Well, for that, we have Gaussian elimination and all of the other robust techniques of linear algebra. So you don't have to worry about it in the long run. In the short run, you have to rely on your intuition and making sure that you engage a new vector in every linear combination.